I think we have one more topic to talk about in terms of number theory, and then we're done with number theory for the semester. At least we're done with the lectures on number theory for the semester. So the one last thing to talk about involves what's called Euler's theorem, and there's a few different ways to kind of approach this. So the first is we're going to talk about what's called Euler's. Remember that Euler, E-U-L-E-R, is Euler, like the hockey team or the football team, the Oilers. So it's Euler's theorem. And what we're going to do first is talk about what's called Euler's totient function. I have no idea what totient means, but this is, anyways, this is what it is. It's defined as, so phi of n. And what it is it's the cardinality of the set. In other words, it's the number of integers from 1 to n. So from 1 to n that are relatively prime with n. So that are relatively prime with n. So for example, if we were to look at phi of 15, what we would do is we would look at all the numbers from 1 to 15. So let me just write it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 15. And then we're thinking about how many of these integers are congruent, or how many of these integers are relatively prime with 15. Well, certainly 1 and 2 are relatively prime. I think it's easier to cross off the ones that are not relatively prime. So 3, 6, 9, 12, and 15, of course, are not relatively prime, so multiples of 3. Let's see, 15 is 3 times 5, so multiples of 5 are also not relatively prime. And then this leaves us with, so let's color these purple. So this leaves us with 1, 2, 4, 7, 8, 11, 13, and 14. So there's 1, 2, 3, 4, 5, 6, 7, 8 of them. So phi of 15 is 8. Okay, so that's how this function works. It's the number of integers from 1 to n that are relatively prime with n. The reason why we include n in there, it seems like we would always cross off this last number, but the reason why we do that is that we get that phi of 1 is 1. Okay, so that's a nice property that we have for the multiplicative, for the Euler totient function for 1. Okay, so there's some nice properties here for this function. You can check that phi of 7 is 6. The reason for that is that if you write out the numbers 1, 2, 3, 4, 5, 6, 7, and you do this again, the only number in that list that's not relatively prime with 7 is 7 itself. And so you have 6 values. This is a property of primes. So if p is prime, that actually happens if and only if phi of p is p minus 1. So if the Euler totient function of some number is that number minus 1, so yeah, phi of 7 is 6, that means that 7 is prime. So this is a way to test primality, or not to test primality. It's a dumb way to test primality, but it's another way to state that a number is prime. So this is what happens for primes. Okay, so this is the Euler totient function. It turns out that there's a nice theorem here, so we'll call this Euler's theorem. Seems like everything is named after Euler, as it should be, because he did it first. So Euler's theorem, and it says that if x and n are relatively prime, so if x and n are relatively prime, then x to the phi of n is congruent to 1 mod n. In other words, x to the phi of n is 1 mod n. So what this means is, let's do an example. So if I were to take, let's say our n is 10, so let's find a number that's relatively prime with 10, say 7. And so we know that phi of 10 is 4, because if you were to write out the numbers 1 through 10, You would cross off all the evens. Okay, so you'd start with crossing off all the evens because 10 is even, so they would have 2 as a common prime factor, and then you would also cross off 5 because 5 divides 10. And you're left with 4 numbers, namely 1, 3, 7, and 9, that are relatively prime with 10. So phi of 10 is 4. And so let's take one of those numbers, say 7, and let's look at what's 7 to the 4th, what's 7 to the phi of 10 mod 10. And so this theorem says that this should be congruent to 1 mod 10. And so what we have to do is we have to calculate what's 7 to the 4th mod 10. Now, there's a small trick here. You don't actually have to compute this integer 7 to the 4th. What you can do is just repetitive squaring. So 7 to the 4th is equal to 7 squared squared. So really, you just have to think about what's 7 squared mod 10. So 7 to the 4th, so let me just write out what we're doing here. We're going to check that that's true. So 7 to the 4th is going to be congruent to 7 squared squared mod 10. 7 squared is, of course, 49. And then 49 is congruent to 9 mod 10. Okay, so you don't really have to compute 7 to the 4th. You just have to kind of repetitively successfully square each of these numbers. Now 9 squared is 81, and 81 ends in 1, therefore it's 1 congruent to 1 mod 10. Okay, so that really is congruent to 1 mod 10. So 7 to the 4th really is congruent to 1 mod 10. So Euler's theorem says that this works for all numbers n as long as the value x is relatively prime with n. This is the theorem, exactly the theorem that gets used in cryptography in a method called RSA encryption. Okay, so again, I'll do a video about that, go into some detail about how that works. Okay, but this is something that's used in RSA encryption. One corollary that I think is worth pointing out, so one corollary, and this is sometimes called Fermat's little theorem. Okay, so Fermat's little theorem. Fermat's last theorem, by the way, was this is the a to the n plus b to the n equals e to the n theorem. So this is a pretty famous result that there's no solutions to this when n is bigger than 2. Of course, there's infinitely many Pythagorean triples, but there's no non-trivial solutions when n is 3 or higher, except, of course, if one of them is 0, like ignoring all the dumb solutions. Anyways, but this is called Fermat's little theorem to distinguish from that other result. And Fermat's little theorem is actually just a really, you could think of it kind of as a corollary of the result, although it's antecedent to it. It came before it, so it's not exactly a corollary, but anyways, Fermat's little theorem says that a to the p is congruent to a mod p for any prime p. Okay, so for any prime p. So this is a corollary to the result before, because what this really says is that a to the p minus 1 is congruent to a mod p. This is the result that comes from Euler's theorem, because phi of p is p minus 1, and a to the p minus 1 is congruent to a mod p. This is true if a and p are relatively prime. Okay, so this is the part that comes from Euler's theorem. But of course, if a and p are not relatively prime, then a is just 0 mod p, because the only values that divide a prime are that prime itself, and so a is 0 mod p, and therefore a to the p is congruent to a, even if it's not relatively prime. Okay, so again, this result right here, that a to the p congruent to a mod p, is called Fermat's little theorem. Fermat's F-E-R-M-A-T. So this is Fermat's little theorem. And this is, you can think of as a corollary of Euler's theorem, even though Euler's theorem came later. Euler's theorem is a lot stronger. It came later.